All right, today we are diving deep into the future of the very software that powers, well, pretty much everything. We're going to look beyond the ideas that built the internet as we know it to see what's just around the corner. For decades, Erlang and its OTP framework have been the gold standard for building resilient, concurrent software. But a totally new era is emerging, one that pushes way beyond those traditional architectures to meet demands that honestly used to sound like science fiction. So let's explore what that future actually looks like. To really get where we're headed, we first have to understand where we've been. And for systems that just can't fail, that story really begins with Erlang and its core philosophy. Now, this famous quote, "let it crash," it sounds kind of crazy, right? Almost reckless. But it's actually the exact opposite. It's this brilliant, counterintuitive idea that it's way safer for a tiny, isolated part of a system to just fail cleanly and restart, rather than let it limp along in some broken, unpredictable state. This was the absolute key to building telephone systems that basically never went down. And this whole philosophy was built on just a few genius concepts. First, Erlang processes are incredibly lightweight, meaning you can have hundreds of thousands of them running at the same time. But the crucial part is that they share nothing. They're completely isolated from each other, communicating only by passing messages back and forth. You can see how that builds resilience, right? If one process crashes, it doesn't drag anything else down with it. And this is all managed by a clever hierarchy called a supervision tree, which acts like the system's ultimate safety net. So how does that work in practice? It's really beautiful in its simplicity. A worker process is just doing its job. If it hits an error it can't handle, boom, it just crashes. A dedicated supervisor process, whose only job is to watch over that worker, sees the crash, and its response is simple: restart the worker from a perfect, known good state. This simple little loop, that is the secret behind systems with 9 nines of availability. But the world has changed. The very definition of scale has been completely rewritten, and the challenges we face today are putting some serious pressure on this elegant model. I mean, just think about it. We're not building for a single data center anymore. We're building for hyperscale global systems that stretch across multiple clouds. We're using serverless platforms where compute resources just appear, do their job, and vanish in milliseconds. We're connecting billions of IoT devices. These are environments OTP was simply never designed for. And at the heart of all these new challenges is a fundamental law of distributed systems, the CAP theorem. It says you can pick any 2 of these 3 guarantees: consistency, where everyone sees the same data at the same time; availability, where the system always responds; and partition tolerance, meaning it keeps working even when the network gets flaky. Here's the kicker. In our global, messy internet, partitions aren't a choice, they're a fact of life. So the real trade-off is always between perfect consistency and constant availability. This really brings the contrast into sharp focus. Erlang was designed for these stateful, long-running processes in a pretty controlled environment. Today, we deal with stateless, temporary functions scattered all over the globe, connected by networks that can, and absolutely do, fail unpredictably. The old assumptions just don't hold up anymore. Okay, so what does the next generation look like? We're seeing a fundamental transformation in how we approach both computation and control in these new, super complex systems. The first big shift is from stateful servers to serverless functions. Instead of managing these big, long-running processes that hold state in memory, we now think in terms of tiny, fleeting functions that just execute and disappear. The actual server hardware underneath becomes completely invisible. For businesses, this means lower costs, and for developers, it means incredibly fast deployment cycles. You'll often hear this called functions as a service. The second shift is, honestly, even more profound. We're moving from orchestration to declaration. We used to have to write out step by step exactly how a system should recover from a failure. Now, we just declare the desired state. We just say, I want 5 copies of this service running. And we let an intelligent, adaptive runtime figure out how to make that happen and maintain it, no matter what fails. But with this massive decentralized scale comes an equally massive problem. How do you establish trust between billions of devices when there's no central authority in charge? The old model of a central server acting as the ultimate source of truth, it just can't keep up. It's a bottleneck, and more importantly, it's a single point of failure that hackers love to target. For something like a global IoT network, this is an absolute non-starter. This new architecture solves the trust problem in layers, so let's just walk through it. At the very bottom, you have the physical IoT devices themselves. They connect through an edge or gateway layer for data aggregation. But the real magic happens right here, in the blockchain layer. This layer acts like a decentralized public notary. It uses tools like a distributed ledger and smart contracts to create a secure, tamper-proof record of who is who and what happened. Only after trust is established here does the information move up to the final application layer. So let's break down the toolkit for this decentralized trust. First, the distributed ledger. Just think of it as a public record book that can't be erased. Then you have smart contracts, which are like automated self-enforcing agreements. To make sure everyone agrees on the truth without a central boss, the network uses consensus mechanisms. And finally, immutable device identities give every single device a digital fingerprint that can't be faked. So we've got new models for compute, for control, and for trust. What does this let us build? Why does any of this matter? Let's look at the incredible applications this all unlocks. We're not just talking about making websites run a little more efficiently here. We're talking about building the foundations for things like the metaverse, these persistent, shared digital worlds where millions of users can interact in real time. This kind of application is simply impossible with previous architectures. Think about the demands for a second. You need to achieve consensus on the state of the world among millions of participants, not just a few servers. You need ultra-low latency so that interactions feel real. And you need the entire architecture underneath to adapt instantly to changing loads and conditions. These are precisely the problems these new paradigms are designed to solve. So, the picture starts to become really clear. We are moving away from systems that we simply command and towards systems that are reactive to events, adaptive to their environment, intelligent in their decision-making, and distributed in a way we've just never seen before. It's not just an evolution, it's a complete transformation. The Erlang era paradigm of supervised, isolated processes gave us the modern, reliable web and mobile ecosystem we all use today. It changed the world. So the question we're left with is, what incredible world-changing applications are we going to build with this next transformation?